When you flip a light switch, you are instantly connected to a power plant that might be hundreds of miles away. From the road, these aluminum lines look static, a series of conductors simply waiting for current to pass through. But distance is the enemy of efficiency. Between the generator and the switch, the laws of physics resist, bleed, and degrade the power. Engineers track this degradation using two primary metrics. The first is transmission efficiency. Every kilowatt that burns off as heat before reaching your house is wasted fuel, so the goal is to deliver the highest possible percentage of what the plant originally generated. The second is voltage regulation. This ensures the physical pressure of the power remains stable, preventing the voltage from dropping when a city turns on its lights or spiking when those same lights are turned off. Operating the grid requires a continuous mathematical response to this physical and electrical decay. Is electrical leakage. High voltage power seeks the shortest possible path into the ground, and the massive steel or wooden poles holding up the wires offer exactly that. To maintain the current, engineers use physical insulators to block the path to the ground. This cross-section shows how a pin insulator secures the live wire. Notice the downward sloping ridges, or rain sheds. During storms, the outer surface gets wet, but deep ridges keep inner surfaces dry, forcing leakage over a long, broken path, preventing power jumping to the structure. Pin insulators manage distribution lines up to 33,000 volts. Beyond that threshold, the electrical pressure will punch through the porcelain or flash over the edges. For voltages like the 132 kilovolt lines on these towering lattice structures, engineers transition to suspension insulators. By stringing multiple ceramic discs together, they build modular strings capable of handling immense mechanical tension and holding back massive electrical forces. These porcelain barriers successfully trap the power inside the wire, but they cannot stop the invisible forces degrading the power as it flows toward the consumer. The wire itself and the air surrounding it actively resist the flow of current through three distinct parameters. The first is resistance. The physical material of the wire constantly converts a portion of the electrical energy into heat. The second is inductance. Because the current is alternating, it creates a fluctuating magnetic field around the conductor. That field induces a secondary voltage that pushes back against the forward flow. The most complex force is capacitance. When two conductive wires are separated by open air, the space between them stores an electric charge. This draws a charging current, creating reactive power that moves through the lines even when no homes are pulling electricity. On lines longer than 80 kilometers, this effect can trigger the Ferranti effect. Under light loads, the charging current causes the receiving voltage to spike higher than the original sending voltage. Because these invisible parameters compound over long distances, engineers use mathematical models to predict and neutralize them. To calculate delivery efficiency, engineers lump the distributed resistance, inductance, and capacitance of the entire line into simplified circuit diagrams. This schematic shows the nominal T method, a common predictive model for medium-length lines. The T model mathematically concentrates the entire line's capacitance into a single midpoint, splitting the resistance and inductance in half on either side. Alternatively, engineers use the nominal pi method for different modeling requirements. The pi model concentrates the resistance and inductance in the center of the line, while splitting the capacitance into two equal halves at the sending and receiving ends. By solving the equations generated by these models, grid designers calculate the exact voltage drop across any distance before a single tower is built. These models serve as the blueprints that make the geographic distance between a plant and a city manageable. These calculations dictate the hardware installed where the transmission line finally meets the neighborhood. The distribution substation serves as the physical endpoint for these equations. The transformers here are calibrated based on the predicted losses. They take the transmission voltage, weakened by resistance and skewed by capacitance, and step it down to safe, regulated levels. This meticulous planning is why a house 200 kilometers from the plant receives the same stable current as a house built next door. The resulting grid functions as a live equilibrium between physical barriers and predictive models. Porcelain rain sheds trap the current within the wire, while the nominal pi and t models calculate exactly how much of that current reaches the consumer.